And we're going to do the standard Proctor, ASTM D698, method B. So what the material requires for preparation is to make sure that we remove the material that is coarser than 3/8 of an inch. We place it making sure that we don't lose material other than what's required. And this sieve is pretty simple to do, but we could do it in the automatic sieve shakers. So the oversized material that is not going to be tested is this type of material that, even though it meets the gradation requirements for granular A, being 1 inch or smaller than that, it would be too large and it would probably have an effect on the results if this was included in the test. So the ASTM method B requires to remove this material and work with the material that is passing through. For oversized material, it could be requiring the use of a 6-inch diameter mold, and that's the ASTM method C. The first piece of information that we're going to need is the weight of the mold by itself, empty and clean. So we're going to put it on a scale that it has been zeroed, and we record this weight. This is the weight of the compaction mold empty, to determine what's the optimal percent of moisture to have to achieve compaction with the same amount of energy to achieve the best unit weight or best densification. So this is the objective, to determine what this water content is and what is the maximum compaction in terms of 100% compaction. Empirically, it's known that the curves are bell-shaped, they're symmetrical around the optimum water content, and so in order to create that, we need to do typically a few points. In our example, we're going to do one demonstration of one test, which will be this point in there. So we're aiming, based on experience, normally we expect the optimum to be in the range of 6 to 10%, so we're going to start dry of optimum at about 4%. And to calculate 4%, we know that the soil, dry soil we're starting with for one sample is in the order of 2,000 grams approximately. So we're going to assume that that material is fully dry, and we're going to add 80 grams of water, which will bring us to an approximate water content of 4%. Zeroing the scale, and we're going to work with approximately 2,000 grams of dried material. We're going to add 80 grams of water. Okay. What that will do is will bring the water content from an assumed 0% to a starting water content of 4% when we add 80 grams. It's not that critical at this point that the numbers are exact, because they will be assessed and measured with more accuracy after. What it is critical is that we do mix the material uniformly, so that's going to take a little time for the material to get uniform water content through. As we mentioned, we place a collar here, and that's going to facilitate the placement of the soil. The hammer itself is this device here. It has a weight of 5.5 pounds, and this drop, which is going to impact the soil, it happens to be 1 foot or 12 inches. So we're going to do it in 3 stages and approximately 1/3 each. 4.5 in height, 4 inch in diameter gives us a volume of 1/30 of a cubic foot. So that would be our volume. In the standard test, we have placed 3 lifts. To each lift, we apply 25 blows or drops of the hammer, and that hammer weighed 5.5 pounds. And we dropped it exactly 12 inches of 1 foot. So if we do this calculation, 3 times 25 times 5.5 times 1 in units of pound-foot, and then we divide that by 1/30, the resultant number is an energy of 12,375 pound-foot of energy per cubic foot. So this is the uncompacted or loose soil. We're going to place that firmly in a stiff surface, like a concrete floor. We're going to hold the mold steady, making sure it's not vibrating loosely, and then lifting the hammer and letting the bottom determine the energy that we're impacting. 1, 2, 3, 4. 25. You notice probably that as I was dropping, I was offsetting the location, and just to make sure that the hammer provides even coverage of the compacted material. And this is the material you end up with. Is 1 lift. It's approximately covering right there, which is about 1/3. This time we're gonna get fairly close, but not quite to the joint. We're gonna probably end up somewhere in there. Again, placing this firmly on the ground, and we impart 25 more blows. Now we have 2 lifts of compacted soil in place, and we're up to 2/3 of the final volume. And we end up exceeding the height because this has to be able to compact down to a minimum of the 4.5 inch height of material. 25. So this is our compacted sample. Remove the color from the mold. And using a straight edge bar, we're going to ensure that the final volume is exactly 1/30 of a cubic foot. And at this point we have the mold plus the wet soil ready to be tested. So again, we zero our scale and we determine the weight of the compacted wet soil plus the empty mold. The two together add up to a given weight. Since we know that the volume is exactly 1/30 of a cubic foot, and now we know how much mass of wet soil I have in there, I can calculate a wet density or wet unit weight of the material. We will now take a sample of the wet soil that is representative, and one of those samples will come from the top of the compacted specimen. This will give us the weight of the dish, cup or container, plus the wet soil. The second sample I'm going to take from the bottom so that we get a representative sample of the whole material. This is another opportunity to see how uniform the compaction went. If you notice with some materials you may have some air voids due to lack of proper compaction. This gives you some certainty that the compaction process worked out representatively. Also, if the material was not thoroughly mixed, you start seeing some dry pockets compared to some wetter pockets of material. This granular material is fairly workable and clean. If you do the Proctor test on a clay material, it will be a lot more challenging. Removing the material out of the cell, and in the case of granular material, is fairly easy to do that because the material basically, as you tap it will come apart. Now this gives you an opportunity. We're missing the ends here because we took water content samples, but as you tear it apart, as the sample comes apart, you can see how uniform the compaction process was. We know the weight of the material because we determined that one in a wet state, but we also, overnight, we're going to get a water content. So we will be able to calculate the dry weight of the material, or the dry mass of the material. So if you take that mass divided by the volume, which is 1/30 of a cubic foot, you can calculate the density of the material. With the water content and with the unit weight of the material, you will get your first point in the curve. So this will be one point that you need to complete in order to build up your compaction curve. Next sample, instead of preparing for 4% in this case, you may go a couple of percentage or 3% higher, so that we end up with another point somewhere there, another point there,